So today I'm going to present the Xolver multi-agent reasoning framework. This is the reference paper. So the key highlights of the paper is this actually proposes a memory augmented multi-agent framework. It actually showcases the how experience driven and collaborative reasoning of expert teams can actually help in solving problems, especially the contribution of different roles to solve a problem, and especially the discussion between different roles different agents who has different roles actually helps a lot in solving a problem. This paper actually highlights that very well. So at first we discussed the architecture. The key This architecture is a very generalized architecture. It can be applied to a wide variety of problems, though they have applied this architecture in this paper to coding problems and math problems. So let's start. At first, the entire framework takes the problem description as input. Then the problem description goes to a planner agent. The purpose of the planner agent is to figure out which roles matters the most to solve this problem. Let's just say you are trying to solve a math problem. So there might be a web analyst, there might be let's just say you are solving a code problem. There must be a tester, there should be a designer, there should be a coder. So based on this planner agent actually, based on the problem, the planner agent actually gives us the roles that is needed to solve this problem. So after we get these roles, we actually spawn different agents with those roles. Like if I had 3 roles, let's just say coder, then this agent will have a coder role, this agent will have the designer role, and this agent might have the tester role. So we'll spawn different agents based on our roles that planner agent gives. So then these agents, they actually solve this problem. Their solution and reasoning trace are generated here, and they actually have the ability to call different tools or different kind of solutions via a Python environment. A Python environment is given to them. If these agents think they need to run a quick calculation, they can actually interact with this Python environment to get some kind of a solution. This is kind of a tool that's a helping hand that helps the agent to make the decision, but the main primary is after they've interacted with the tool, they can get to a solution and they generate the reasoning and the trace here. This reasoning trace and then goes to a judge agent. The purpose of judge agent is to judge these responses. He takes each of the response and based on the problem statement, he actually scores each of the response, and based on his scores, these parts are actually these solutions are actually ranked here in an intimate shared memory. So this is actually kind of like an LRU cache. So the one with the highest score is actually kept at the top, and the one with the bottom score is kept in the bottom. So if a new trace comes that is like has a higher score than the bottom one, then the bottom one gets eliminated. So this is how they maintain a cache of the best reasonings, and these reasonings are then actually fed into all of these models. They all see each other's reasoning. So now they can actually reason over this and they can change the response. So these loops goes on couple of times, and after these loops goes on couple of times, the final result, then we actually after like just 10 iterations, we pick the top result from here and actually give it to a verifier agent. The purpose of the verifier agent is to actually do first of all, let's just say the judge agent actually does not run the code. Let's say you have a code. Judge agent does not run the code. It just simulates the running. He looks at the code and he just generates output based on simulation he generates, but he actually doesn't run it. Here we can run the code. Verifier agent does a lot of things. It can run the code, but typically they don't run the code. Rather, they actually run a check on like whether this is syntactically, semantically correct. And it can also do something like if it's a math problem, it just checks whether this problem has the output format is right or not. Some kind of basic verification is run, and when the verification is complete, it actually gives the final output. If verification fails, then we actually pick another result, the second result, the third result. That's how we actually pick the best one that actually passes the verification. This is the final output. So we actually missed one part, and that's the episodic memory. Before the we actually seen how the intermediate shared memory actually helps the agents with reasoning. We also have another one is called the episodic memory. The episodic memory has two key components. It actually, so first of all, before any problem, based on the problem statement, we actually do a kind of a RAG-based solution where they actually bring in similar problem solutions from the internet and build a memory system. Okay, so let's just say you have a coding problem of like some kind of lead code problem. Then you actually take similar problems from the internet and keep in this memory, and this memory is a kind of a RAG-based memory, so the LLMs actually get a kind of a RAG-based context from this episodic memory. This is the first part, and the second part is they actually use this final output. The final output that we just got here was also actually fed into this episodic memory to enrich the episodic memory with the outputs that are actually verified. So this is how this entire system works. As I said before, the main benefit comes from the multiple roles, which you can see as being spawned by this planner agent, and the another thing is discussion, which is being enabled by this intermediate shared memory. And the third part is the episodic memory, where we can see we'll see later that RAG-based retrievals actually improve the performance by quite a lot. Also one thing, the authors actually made sure that the exact problem here that we should try to solve is not present in this episodic memory. If that happens, like it just gets the answer from the internet, right? So that's not a valid judgment. So the authors actually made sure the problem statement he's feeding here does not exist in the episodic memory. So this is the architecture. So as we've seen before, the architecture that actually has 4 main components. So I'm going to rerun through them again. So there's a planning agent who actually spawns different roles. There is a dynamic reasoning agent, which are these agents who actually does the main reasoning task. Then there's the judge agent, who is here, who actually judges the response. And there's the verifier agent, who actually verifies the final output, whether this is correct or whether this actually follows the correct format. This is the purpose of the verifier agent. We actually have 2 memory type: episodic memory, which is from the internet, which is previous solutions, and we have the intermediate memory, which is kind of enabling the shared discussion between these agents. So they ran this architecture on multiple data sets like GSM 8K, AIM 2425, Math 500, and Live Code Bench. We can see they have compared it to different top tier models like Grok, Gemini, and Gemini 2.5 Pro. In this, among the models they've selected in these benchmarks, Gemini 2.5 Pro is probably the best one. O1 is the best one. O1 is the best one. Now we'll see how Xolver improves the performance. I missed one thing. These agents, these dynamic reasoning agents, they actually use the same LLM with different roles, different system prompts, but all of these agents, including the judge agent, all of these agents use the same LLM under it with different system prompts with different roles. Okay, so I think that needs to be clear. So they applied Xolver to 2 different models. One is O3 mini medium and another is QWQ 32 billion. So now if we look at the results, we can see here's the Xolver result. The overall Xolver performs really well. Let's just look at this, like GSM 8K, Xolver, okay, so Xolver plus and Xolver minus, what does that mean? That's something. So the Xolver plus is something with the episodic memory, and Xolver minus is without the episodic memory. So you can see like this part does not exist for Xolver minus, and does not exist for Xolver minus, and exists for Xolver plus. So okay. So here we can see Xolver plus performs 97.1 in GSM 8K. That's more than O1. So O3 medium is we know all this is a very lower tier model. Let's just go for the open source one. I think these are the most interesting. So QW30 scores 98. O1 is 96. You can see like this is a huge model. This is a big model from one of the best vendors out there. But PUWQ with Xolver actually beats it. That's a big statement, I think. Then you have, let's just say, then we can see like it actually beats it in couple of places like AIM25. Overall, the performance is actually really great of Xolver. You can look at the results later. So so we understand like Xolver performs really well, but why does it perform well? This is why I think the paper actually shows its class. They actually analyzed it very well why Xolver performs really well. So first place is they actually measured the contribution of different components. They eliminated one by components one by one and checked the performance. Like in the first, this is the first. You see, they actually did we actually told you before like there's a multiple iterations going on. They generate response, the judges, and they go again. This loop goes on a couple of times. They actually say what happens if we just remove this multi iteration, right? We can see a 23% drop and almost 7% drop in live code bench. So that's huge. Then they actually remove the multi-agent part, where they actually kept only one agent. This is why we can see a huge drop. And then we have the judge agent, where they have removed the judge agent, and instead of judging another judge agent judging it, different part, this LLM, this reasoning agent, they judge their own response. If we remove the judge agent and introduce self-judgment, then we can see 9.9% performance drop. So this is a really nice thing that just shows how these three components contributes hugely to the performance increase in Xolver. Okay, so another evaluation, important part of the evaluation study was they thought, as I told you before, like Xolver plus and minus. We eliminate the Xolver plus, then we have the episodic if we remove the episodic memory, we have Xolver minus, right? So we can see Xolver plus performs better than Xolver minus, but they actually went further and analyzed how different retrieval techniques impact. So they did a no retrieval where they actually remove the retrieval, it's Xolver minus. So and then actually introduced self retrieval where the LLM was prompted to gather similar problems reasoning from its knowledge base, and then giving the problems from the internet with a RAG. We're actually giving it, we're asking the LLM to self retrieval. It just generates things out of its memory. It generates similar problems out of its memory. So this is self retrieval and this is external retrieval. We can see external retrieval actually outperforms both no retrieval and self retrieval very well. So this actually shows the importance of RAG in this framework. Then another part was so another key analysis is like, is Xolver consistent? What will happen if I just shuffle the data? If we do like shuffling. So as you can see, there is the episodic memory actually grows with final output. So actually you have to remember this final output is not only the correct solution, it contains the both correct and incorrect solutions. Alright, if verifier passes, we just put it in the episodic memory, right? So this is not something you can say like we're only putting the correct solution. No, we're actually solution where this does not know the level yet. We don't know here, we don't know the level. If the model says this is my final answer, we just put it in the episodic memory. So this is a key distinction. So we can see here that there should be an impact of the data orientation of the data order. We can see that there should be an impact. So they have actually shown whether this is true or not. So they have shuffled the different data sets and they run it 5 times. So when they run it 5 times, the mean is 97.6 and the standard deviation 1.6. So we can see the standard deviation is very low. So this shows that yes, it might seem that the order matters, but the order actually doesn't matter because in different orientation, the performance has a very low standard deviation. Okay. So again, another part of the computational complexity, the computation is O of ml, because it's these agents we can actually inference them in parallel, so you can say that the inference time will be 1 here. So is equal to, the inference time will be equal to the, if we use one agent, if we use multiple agents, the inference time will be equal to the one agent. So this is what this says. And the final part is the this is the part that made me the most interesting. They actually analyzed what type of reasoning pattern actually helps the problem. Okay, so they took this reasoning traces and they inputted it into another LLM and asked it to identify different reasoning patterns in the reasoning trace. So based on that, they did some analysis and they reported which reasoning traces, which reasoning patterns mattered more. So we can see the self-evaluation and new approach. This type of reasoning patterns actually increases when the problem's difficulty increases. I think this is very self-explanatory why self-evaluation is important and new approaches are important for difficult problems. So that's the entire paper. So the key essence of this work for me is a generalized architecture. It can be applied to different various types of use cases. I have already applied to a couple of my ML projects, and the results actually stand up because every time I apply Xolver, I saw improvements and in my different ML projects. So that's why I actually like this paper so much. It can be applied to wide variety of use cases, and the best part is you can see the QWQ model almost performs equal to O1 or Gemini 2.5 Pro. So this is a really big achievement for open source LLMs. So that's all from my end, and thank you for watching.